Hello students, welcome to the course Network Theory. In the previous video, we started off with Norton's theorem. We have proved it is a dual of the Thevenin's theorem. Okay, and also we solved one example how we solve using Norton's theorem. Okay, so today we'll look into the more problems in Norton's theorem. Okay, so note down the second problem in this. Okay, obtain Norton's equivalent circuit for the network shown in figure. Okay, so note down the figure. You have 2 ohm in parallel with 4 volt, 3 ohm, 10 ohm in series with 1 ohm, 8 ohm, and a load. Okay, so how we solve this? Okay, so first looking into the picture, so you have to identify so independent sources, dependent sources. So it looks like a simple independent sources are present, and there are two trivial elements are there here. Okay, if you observe, there is a 2 ohm in parallel with 4 volt. Okay, and there is a 10 ohm in series with 1 ohm. No need to remove them, but you should know they don't have any much significance here. Okay, so they don't have much significance. Even you can remove, even you can keep it. So you have to consider that it is the same voltage across this, it is the same current across this, it does not affect any much. Okay, so there is a trivial element, equivalent characteristics. Okay, you can remove and write also if you are confusing. Okay, so we'll solve the problem. So what is the first thing? So the load we should remove. Okay, so because no need to find out any current or voltage here, just they have shown a load is connected, so you have to remove the load and you have to short circuit this to find the short circuit current. Okay, so hope you are noted down. Okay, so to find Norton's equivalent circuit, load is removed between the terminals AB, which is the steps are similar to Thevenin's. Okay, and here also we have discussed the same. And since 2 ohm is connected in parallel with 4 volt source, has no significance and can be neglected. Similarly, 10 ohm connected in series with 1 amp current source is also neglected. Okay, so final equivalent circuit looks like this: 4 volt in series with 3 ohm, 1 amp, 8 ohm, and AB. So circuit B is removed now. Okay, so now this is the circuit. Okay, so now what you have to do? You have to find the Norton's current, that is IN, which is nothing but the short circuit current. So you have to short the terminals AB and you have to find the current, short circuit current, ISC. Okay, so you have, so far you have learned source transformation, mesh analysis, node analysis. Okay, so any of these basic concepts you can apply to solve here for the ISC. Okay, so till here you note down. I will go further. So first step to find IN. Okay, so short the terminals AB for that circuit. Okay, so this is AB is near nothing but here also it is shown. Okay, so why I have shown here? Because it is at the same potential. I can apply the node analysis. I'm using the node analysis technique to find here. So when I am finding node analysis, first I should find the node voltage and then I have to find the short circuit current. So what is this here? So short circuit current ISC is nothing but this branch current, right? So this branch current is nothing but, if you consider this as VA and this is the reference node, so it is at ground potential. So VA minus VB, which is VA minus 0 by 8 ohm, that is the ISC. For that, first you need to find the VA. So you write the KCL here. So write the KCL, how it will come. So you have 3 branches. So we assume that all the currents are leaving the node. Okay, so this is the normal assumption. We will make it in node analysis. Okay, so if you look at this branch, so here there is a 4 volt and there is a VA. Okay, so VA minus, how you write? VA minus, so this equation I have not written, I always write simplified one. You write this. Okay, VA minus 4 by 3, then current leaving only it is there, so that's why it is no need to bother, plus 1. Here you can consider in terms of ISC or in terms of VA by 8. Okay, VA minus VB by 8, anything you can consider, plus I will consider in terms of VA itself. Okay, VA minus 0 divided by 8 equal to 0. This is the KCL equation or node analysis. Okay, so all the things are written in terms of current. So now what we'll do, we'll group the VA terms separately and the current terms will separately. Okay, so here I have VA by 3. Okay, so VA by 3 plus another VA I have here, VA by 8. Okay, only VA terms are remaining. I will take it right side. So if I take here minus 4 by 3 is that. So if I take right side, it will become plus 4 by 3. Then here plus 1 is there. I will take it as minus 1. And here minus 0 by 8 is there. It does not have any significance. So this is the final equation you get. So now you have to take the LCM and solve for VA. And then take the ratio VA by 8. You will get the ISC current. Okay. Hope you noted down this. Okay. We'll go further simplify this and solve the ISC current. Okay. So I will erase and go. So you pause the video and note down. Okay. So that is what I have shown you straight away. It is grouped now. VA terms are grouped here. Next step. So 1 by 3 plus 1 by 8 VA, 4 by 3 minus 1. So here it is 8 plus 3 by 24 VA equal to here 4 minus 3 by 3, which is 1 by 3. Okay. You can show that in this step also. 4 minus 3 by 3. If you have written there two steps, third step you can write like this. Here VA terms are grouped. Here this one you have taken. So then you will get 1 by 3. Okay. So now what you will get here 11 by 24 VA equal to 1 by 3. Okay. Therefore VA equal to, so it is 1 by 3 already is there. So 24 will come in numerator and 11 will come in the denominator. So 24 by 11 into 3, which is nothing but 24 by 33, which is, if you do the calculation, calculator use, you will get the 0.727 volt. Okay. So that is the idea, or you can keep like this only 24 by 33 volt. Okay, units you have to mention 24 by 33 volt. Then ISC. So ISC is nothing but VA minus 0 by 8, right? So that's what it is following. So VA we will substitute now. So 24 by 33 by 8. Okay. So solve it. So what you will get, or it is 0.727 by 8. So when you solve it, so in the calculator it will give you 0.0908 amps. Okay. So you verify it. So you are getting the same answer or not. Okay. So this is the first part of the Norton's. Okay, this ISC is nothing but the Norton's current. Okay, IN. Second part is finding the ZN, that is the Norton's equivalent impedance or Norton's equivalent resistance RN, which is same as to RTH finding. Okay, so you have to deactivate the sources and you have to find the equivalent resistance. Okay, so we'll do that. So to find RN, deactivate all the independent sources. So you had a current source which is open circuited and you had a voltage source which is short circuited. That's why the circuit becomes like this, simple. Okay. So here you had a current source. It will become open circuit. It does not have any current flow here. Okay. And here you had a voltage source which is nothing but 0 volt. It is a short circuit. So remaining is 3 ohm and 8 ohm. So how they are connected? Series. So that's why just added them 3 plus 8. So you have to look from here for the Rn. You have to write like this. Okay. So Rn is equal to 3 plus 8, 11 ohm. Okay. Or RAB also will call. So now just the Norton's equivalent circuit is current source in parallel with the Norton's equivalent resistance. So current you got is 0.0908 amps and this is 11 ohm. Simple. Okay, so this is how the Norton's problem comes. Okay, so in both the first problem and the second problem we have seen only Norton's equivalent circuit. Okay, so now if something load is connected, so we need to find the value of voltage or current across that, right? So that part we'll consider in the next problem. Okay, so hope it is clear till here. Okay, we'll go for the third problem now. Note down this question. Find I naught in the network of figure shown using Norton's theorem. Okay, even you have to identify the load here. Okay, so you have 2 kilo ohm, 6 kilo ohm, 3 kilo ohm, 2 kilo ohm, and 4 kilo ohm, and you have one independent voltage source 12 volt. Okay, and you have to find the I naught in this branch, that is 2 kilo ohm branch. You have to find the I naught current, meaning what? This is nothing but acts as a load now. So you have to open this. Normally it will come right side, right? So now it is upper side, it has come. So you have to open this terminal. Okay, and you have to find the IN and RN from looking into the top. Okay, so how they are connected, accordingly you have to find. Okay, so note down this question. Okay, so we'll solve this. Okay, first step. So I naught means it is a load current. this acts as a load. Now we will remove. We are interested in I0, hence the 2 kilo ohm resistor is removed from the circuit diagram of figure, which acts as a load. So the resulting circuit diagram looks like this. Okay, so when you have such a figure, so what you will apply here? Okay, so which method will suitable for you, so that you need to do. Okay, so if you consider this completely, it is open circuited. Okay, so you can apply the node voltage analysis, or you can apply the KVL. Okay, so just note down this figure. Okay, so how to do that? So to find IN or ISC, short the terminals AB. Okay, so now to find IN, what we have to do? We have to short the terminals AB. Okay, so which is open, which is having 2 kilo ohm. First we have removed. Then to find IN, we have again shorted it, and we called it as short circuit current, which is nothing but a Norton's current itself. Okay, fine. So now we have considered here. Okay, so there is an ISC current. Okay, KCL we are applying. So there is a current, total current leaving from this node is ISC. Okay, which is divided here according to KCL. I call it as current I1, and this side it is I2, I call it. Okay, so again they will join together, it becomes ISC. So now we will identify this as two nodes. Okay, V1 and V2. Okay, so we call it as V1 and V2, and here we consider it maybe as a ground. Okay, so it is at the ground potential. Fine. Okay, so how it will work? So now V1 by inspection, V1 with respect to ground. Okay, sorry, this is not the ground, or this is the ground. Okay, so this is the ground. So by inspection, so this is connected at the V1 minus 0, right? So in the same potential it is connected, that's why it is plus 12 volt, V1 equal to 12 volt, just by looking into the circuit. Okay, so now we'll write the nodal analysis for V2 now. So V1 you got, so we'll apply for V2. So applying KCL at node 2, we have V2 minus V1 by 6k, which is at left side, plus V2 by 2k at the downside, plus V2 minus V1 by 3k. Okay, so how it is considered here? We have not considered again third circuit. Okay, here I not consider V3, but now I have considered this as completely V1. Okay, like this. So V2 minus V1. This is V1. Here, if some elements are connected, then you would have considered here V3. Since this is at the same potential, even this will act also V1. Okay, so just to show you, here also it is now V1. Okay, no other difference here. Fine, because no elements are connected, just a short circuited, that's why it is only V2. So that's what V2 minus V1 by 6, V2 by 0, 2 kilo ohm, V2 minus V1 by 3 kilo ohm, same. Okay, we have considered V1 you got 12 volt, you substitute that in the equation, and resistors are given in kilo ohm here, so you write the current straight away in milliamps, or every time when you write in equations 3 into 10 to the power 3, like that you have to mention. Okay, it is your choice. So now we have written this equation V2. Now we will group the V1 and V2 terms. Okay, so V2 by 6k I have, and then V2 by 2k I have, and V2 by 3k. So straight away I have grouped it, so to avoid the number of steps. Then V1 I have separated, and right side I have taken V1 by 6k and V1 by 3k. Okay, so now I know the value of V1, but before that I am simplifying this. What I am getting, so it is 1 by 6, 1 by 2, 1 by 3. So take the LCM, it is 6k. Here it is 1 plus 3 plus 2 it will come, which is also equal to 6. Straight away I have written. So it is nothing but V2 you will get. Okay, left side it will be V2 into 1. Here you have 1 by 6 plus 1 by 3, which is nothing but, so 6 LCM. So you'll have 1 plus 2, 3 by 6, which is nothing but 1 by 2. Okay, so that's why 1 by 2 into V1 is written. So now we know the V1 value. So just we have substituted 12 volt. So V2 is 1 by 2, 12 by 2 is equal to 6 volt. So now you got the node voltage. So once you got the node voltage, so now you can easily find the ISC current. Okay, so which is the current, right? So we need to find out here. Okay, so till here you understood. So how you write the KCL and how you solved it and substituted V1 and got the V2. Okay, so this is very simple numerical. Okay, next part. So referring to the figure, we find that by applying the KCL there. Okay, ISC is nothing but what? I1 plus I2. Right. So what was there I1? It is V1 minus V2 by 3K. 1. Okay, so here we have taken I1 and I2. So this is V1 minus V2 by 3K. And another is this is V1. Right. This is also at same potential. So V1 by 4K. That is I2 current. Okay, both we are added. So just substitute here V1 and V2. So what you had V1? 12. 12 minus 6 by 3 plus V1 is 12 by 4. Okay, so what you will get? So it is 6 by 3, nothing but 2. 2 plus 3, 5. So while writing answer, written 5 milliamps because it is kilo ohm is there. No, 1 by kilo is milli. So 5 milliamps is the answer. So these steps I have not shown. Okay, you add it. Okay, so you write this 2 plus 3. So that's why ISC IN equal to 5 milliamps. Okay, clear? So this is the first part. So now find the second part. So deactivate all the independent sources now. So what we had, one voltage source was there, it is short circuited now, and now I have the combination like this. Okay, so this is the A terminal now, and this is the B terminal. Okay, so you have to find so which way they are connected. Okay, so you have to find out the combination of this. Okay, how they are connected. So to find out that also you can use the method of some junction names you can give. Okay, so A to B, you have to rearrange this equation or circuit so that you will get the, so we'll see in the next figure. Okay, so how we find out this Rn. Okay, so AB we have taken there. So what you had there is 6 and 2 kilo ohm are in parallel, which is in series with 3 kilo ohm and 4 kilo ohm. So 6 and 2. So by looking into the A, okay, so how we look at, by looking from A, so these 6 kilo ohm and 2 kilo ohm are in parallel. So these two are in parallel here from this terminal. Okay, one is connected from here to here, one is connected through this resistance to here. Okay, and then this is in series with this. Clear? So once you solve this, so this complete is parallel with this, right? Complete is parallel. So this is one branch, 6 kilo ohm in parallel with 2 kilo ohm. Okay, so this same thing can be written like this. Okay, so if you have like this, okay, so one resistance is here, that is 6 kilo ohm. You have another resistance here which is 2 kilo ohm, and here you have the 3 kilo ohm, and then you have the 4 kilo ohm which is like this connected. Okay, and you have to find the resistance over here, AB, RAB or RN. Okay, so this same thing I have written like this. Okay, 6 kilo ohm parallel with 2 kilo ohm, 3 kilo ohm, and whole is parallel with 4. So the just I have rotated the circuit horizontally. Okay, so hope you are understanding this. Fine. See here, this is what I have written: 6 kilo ohm in parallel with 2 kilo ohm in series with 3 kilo ohm, and the whole this one is parallel with 4 kilo ohm. So you are finding the RN from here. Okay, so this is the Rn you are looking at. So by looking at, so now how they are connected, you have to find out 4 kilo ohm in parallel with this whole. I have put a big bracket. Then what you have, 3 kilo ohm plus this is in series. Now we are back in parallel, 6 kilo ohm and 2 kilo ohm parallel. Okay. So now you have to solve this. Okay. First you have to inner bracket you have to solve. So 6 into 2 by 6 plus 2. Okay. 12 by 8 it will come. That you have to add with the 3, and that solution you have to multiply with 4 kilo ohm divided by that. Okay, so parallel connection you have to find out. So simplification is much. So far you are getting Rn very easily, right? So now you got a some complex network. Okay, so that is what, so 6 into 2 by 6 plus 2, every time kilo ohm I have removed now. So finally we will write the kilo ohm. Okay, so it is 1.5 we got. So 12 by 8 you will get. So 4 2 is 4 3 is 3 by 2 means 1.5 kilo ohm. That is added with 3 kilo ohm, it becomes 4.5 kilo ohm. So 4 kilo ohm and 4.5 are in parallel. So multiplied 4 into 4.5 by 4 plus 4.5. So which is 18 divided by 8.5. So which it will give you 2.1812 kilo ohm. So that is the Rn value. So finally you got the Rn and ISC value. So draw the Norton's equivalent circuit for the given circuit now. Okay. So this is the Norton's equivalent circuit. So current you got as 5 milliamps, which is in parallel with now Rn, which is 2.12 kilo ohm. Okay. Thevenin's voltage source in series with resistance was there. Norton's current source in parallel. Okay. So little computation was complex here. Other than that, everything is simple, right? So fine. So now what we have to do? So far in previous two problems, we will stop over here, right? Now they have told you to find out I naught current. That means there is a 2 kilo ohm load. We have to connect it back, and you have to measure the current across this branch. Okay, so which will be very simple. Current divider rule, you can solve it. So that part we will take up next. Okay, so hope you have noted down this. Okay, so to find I naught, so we'll reconnect the load 2 kilo ohm. So now if you see, so this is the total current coming over here, and now this is splitted among here. Okay, so here one current, here one current, but we are not interested in finding this branch current. We are finding interest in this current. That's why what we have to do, we have to apply current division rule. Okay, so total current I 5 milliamps into opposite branch resistance, which is 2.12, divided by total resistance 2 plus 2.12. Okay, so that is what written over here. 5 milliamps into 2.12 divided by 2.12 plus 2. So kilo ohm get cancel out. So what you will get, use the calculator here, 2.12 by 4.12 into 5. So you'll get 2.57 milliamps. Okay. So this is the final answer. Okay. I naught. Okay. So in the previous problem as well as this, so we have solved the problems involving the first step, RTH finding, just deactivating the voltage sources. So in the next case, we'll take the remaining two cases. If the dependent source is present along with independent source, and if there is no independent source at all, only dependent source and resistor combination is there. So that we have done in Thevenin's also. Similar way, we'll do it in Norton's also. That we'll see in the next video. Okay, so hope it is clear. So go through once again. Okay, so we'll take up the next problems in the next video. Okay, thank you.